a couple of seats left, I guess, over here and over here and here. So there's more room left. And of course, you are also able to sit on the stairs if you like. Okay. All right, welcome back, everybody. So if the last talk was about working on cars, it's pretty great because Willem van Hulle here has been working on trains. So look at that. That's the Rust mobility crowd. Amazing. And Willem here, he's from Belgium. He will talk to us today about stream operators and how to make your own. So please have a big round of applause for Willem.
Hello, hello, hello. It's okay, the sound? Yeah. Okay, so can you present project? Okay, thanks. So I'm Willem van Hulle. I'm a software engineer from Ghent, Belgium. And today I want to show you a bit how streams work in Rust and how you can make operators for streams, so transformations of existing streams. The slides contain some links, so if you want to follow the links, you can go here, and yeah, you can read the references that I mentioned. So why did I get started with streams? So I forgot his name. I started with trains last year. Last year I was working with trains, and trains are moving vehicles that are sending out data, video streams, audio streams, but also other kinds of streams. And I had to process these streams somehow. And yeah, obviously streams in Rust are useful for that purpose. So first of all, there are three. You could say there are several kinds of streams. There are the actual physical streams that contain the actual data, the electrons, the photons who are flowing through the cables. We're not going to talk about that today. There's also the leaf streams, which are a bit like leaf futures. These are the futures that don't have any other future beneath them. And leaf streams are the streams that don't have any other stream behind them. And they usually correspond to streams provided by the async runtime that are very close to the operating system. But today will be more about stream operators, so the yellow one. And I try to be consistent in terms of colors and shapes, so you could maybe help for you to follow along. So the operators are always going to be yellow, and streams are going to be blue, and data is going to be purple, red. And the stream operators we'll see today, we'll see the basic ones from the futures crate, like map. But to show you how to build an operator, I'll show you two examples, two example operators. A double operator that just doubles an integer stream, which is quite simple, and a fork operator that can branch a single stream into multiple output streams. So let's get started. Maybe a good way to start is how would developing code for trains look like if you don't have streams? If you do it in a naive, imperative way, you get probably you're gonna initiate a connection, for example, a TCP stream. It's just for example purposes, and you're gonna loop over the items that are yielded by this stream, and you're gonna match, and you're gonna do lots of stuff, and it becomes very nested and hard to follow along. Also difficult to test things independently, things that are not related, but it's necessary to only test specific things and not everything at once. So what you could do is switch to the stream trait in Rust and stream operators. So instead of looping over each packet of data, you're going to filter the data or map it and use the typical operators that you know from iterators, but you're going to do it for an async stream. And then there's this quote, programs must be written for people to read. So usually people are more often reading code than they're actually executing. I mean, that's just it's just a quote, but I think it's clear from this example that the code is much more linear. There is no indirection, no jumping around. You can just follow along from the top to the bottom. So it's a bit easier to maintain. But before we can start about operators, we have to know what is a stream in Rust, because stream has many meanings. But in Rust specifically, in the futures crate, the stream is just a trait with an item type and a poll next method. It's basically a combination of an iterator and a future. So the next method is kind of async. And the meaning is similar to futures. You probably already work with futures. However, there's one tricky thing, and that's that when it yields none, it means that the stream is currently exhausted, but it may yield another item in the future. So that could, for example, happen when you have a channel receiver, and the channel receiver notices that the queue of items waiting to be delivered is empty. Then it would yield ready none, for example. So how do you build, how do you work with stream operators? Well, you just build pipelines. So you will start with a source, and then you apply operators to it. And it's quite easy to see in the diagram. Go from left to the right, directly mapping the data. And also in the code, it's quite easy to follow along. So that's the nice thing about streams in Rust. But something you may notice here is the filter method, the filter operator. It takes an async closure. But if you don't like async closures or async blocks, you can just use the ready function, which turns the output of a Boolean into an async Boolean. It's a nice function that exists in the standard library of Rust, and it looks very simple, not very useful, but if you would use async blocks or async closures, the output stream that you obtain after filtering or mapping becomes easily not unpin, and it can be a bit annoying. If you just use the ready function, it makes life easier, and you don't have to box or pin stuff. Okay. Now, the first example is going to be a simple example. We're going to try to build an operator. And one of the most simple things you can do is take an integer stream and multiply each value of the integer stream. So it's very simple in concept. But we'll see, I'll show you a bit the things that you always have to do when you build stream combinators. So the first thing you have to do is you build a struct or something that wraps the input stream. It has to be generic over the type of the input stream, because in the end, you don't want the user to have to know about the actual input stream. You just want them to be able to double stuff without knowing or providing which stream exactly is the input stream. So it has to be generic. And then you have to implement the poll next method. So we could start naively. You probably have heard about the pin type and the poll type. They're quite hard to understand. For me, they were very hard to get my head around. But the first thing you could try is, well, we put the input stream as a field in this struct, and if you want to turn this struct into a stream, you could say, okay, we will just forward calls next to the inner stream. But the problem is you can't do that just like that, because there is a pin around self. So inside the trait of a stream, the method that is required, the poll next method, the first argument self is of type pin mute self. And this pin is protecting the fields of the thing it is wrapping. So we can't just execute this code. This code is not going to compile. So what should we do? Well, the reason we cannot do it, we cannot remove the pin, is because the input stream might be not a pin. And we have to get around that. So, okay. So we have the argument self is of type pin mute double, and we somehow have to get to the input stream and then poll it. So we have to kind of we have to remove the pin somehow. But then we have a mutable reference to double, and then we can have a mutable reference to the field, and the field is of type input stream, and we know that if we put a pin around it, that we can poll it, and then we have actually solved the problem. Again, try to be a bit consistent with the colors. So purple blue is the pin type, the operator is yellow, and the input stream is light blue. Okay. Now, if we would just try using the getMute method, the getMute method is a method that works when we know that the input stream is unpin. We have a problem again because we can't put a pin new around it in the step on the right to be able to poll it. So we need to find another solution. And you could say, okay, we just put the unpin as a constraint on the input stream, but it's not a very good way to solve this problem. Okay, so why does pin get mute require unpin? Well, if you would allow pin to be converted into a mutable reference to the thing it wraps, you would be able to swap the thing that is behind the pin and effectively move the data, which is forbidden by pin. So you can't unpin anything. The pointer inside, the reference inside, has to point to something that is unpin to be safe. So we only allow getMute when T is unpin. Yeah, I have a silly analog here, like an unpinned bird is safe to move, and you can put it in a cage with pin new, and you can get a mutable reference to it using getMute. Examples of unpin types would be all the primitive data types, also things that don't have any self-references. So almost everything is unpin. On the other hand, the not unpin things are the things you can't easily move. They're dangerous to move, and moving them would cause problems. So for these kind of types, you can't apply the getMute method. And examples of these types are, for example, self-referencing types like the state machines that are generated by async blocks, or data types with self-referential pointers. So, however, this is kind of rare, since most basic types are unpin. But as soon as you start working with async, with futures and streams also, you have to know a bit about that. So, as I said, one workaround would be to just only constrain the input streams to the input streams that are unpin. So we would add this constraint. But yeah, then users always have to make sure that their input streams are unpin. And that's not a good way to distribute new functionality. So how to support input streams that are not unpin, that are maybe self-referential, created with generators, for example? Well, there's a trick, of course. There's many ways to solve it, but one way is to just put the input stream on the heap and put a pin wrapper around it. So then you obtain a pointer to a location on the heap, and the pointer is safe to move because it's just a pointer to something in an unrelated or separate data structure. But it dereferences to the original input stream, so you can treat it like the original input stream. So this is a way to make something that is not unpin. So you could do that as well for the stream. So instead of just having a plain field of type, the input stream type, you put a pin box around it. So this will turn this field into something that is unpin. And because unpin is an auto trait, also the double strike becomes unpin, and the operator is unpin. And once we have that, we can just call getMute and also asMute. Maybe another illustration. Yeah, sorry, it's very crowded. But yeah, so we, instead of having just a plain field input stream here, we have now a box and a pin around it. So the box looks like a square, and we have a pin around it. So instead of just being directly embedded in the yellow operator, it also has a box and a pin around it to make this whole thing unpin. And because it's unpin, we can apply the getMute method because it's a nice type, it's an unpin type. And once we apply the getMute, we have a immutable reference to double. We can get the input field, and then we use a special function method called asMute to turn the pinbox input stream in a pin mute input stream. So then we have what we need, and we can just call poll next on that. So this is mainly two big steps. First the getMute and the asMute. Okay, so the complete implementation would look like this. Now for the stream method, so this turns our operator into a stream. So we have two ways now. Either we put the unpin constraint, which is maybe not so nice, or we just box things. We just box the input stream. But there's a third way that I can't mention right now because of lack of time, and it's the pin project crate. And this is the one that is used by most stream implementations or operators on crates.io, for example, in the Tokyo crate and so on. And that one uses macros to provide a safe projection from the operator struct into the inner stream. However, yeah, to be able to understand the implementation of this safe projection, you have to know a lot about macros, and I don't know much about that. So I skipped this one, and I just show you how to do it with the boxing. So this one. So how do you distribute an operator? So now we have a struct that behaves like a stream for any input stream. So we almost have an operator. We still need an extension trait, and an extension trait is the standard way to distribute stream operators. So you're gonna have to provide a kind of constructor that turns any stream that has the right constraints, so items are integers, and turn it into a doubled stream. And besides that, you need to implement this trait automatically using a blanket trait. And once you have that, you can put it inside a crate, ship it, and the end users just have to import that trait, and they can call the double constructor on any compatible stream. Okay, then there's another example, which is a bit more complicated, 1 to n. So let's say you have one input stream, and you want to turn it into n output streams. I encountered this problem more for like 1 to 2 or 1 to 3, but I thought maybe it would be nice to generalize it and learn a bit more about streams and futures and async runtimes and so on. So as a hobby project, I built a cloning operator for streams that can clone input streams for which the items are cloned in a lazy way. It's a bit like a channel, but yeah, not completely the same thing. It's more really a stream operator. There's, however, some complexity. So you have the typical complexities from futures, but also the ones from iterators. For futures, for example, if you implement futures, you have to think about the behavior when a user that is polling suddenly cancels or drops the future. You also have to think about the wakers. Where are you going to store the wakers? And then there's also the iterator aspect. you want the ordering to be consistent among different consumers for output streams. And you want also to be able to deal with slow consumers. So if you have n output streams and there's one who is really slow, you don't want the whole program to panic and crash because of memory issues. So yes, I already said that I encountered this when like 1 to 2 or 1 to 3, like a small number of n. But I was working with the train data, so the train data had some latency, and the latency had to be processed in 2 different locations on different tasks or threads. One would be the UI for the front end, where you display the latency, and one would be in the backend, where you engage breaks or emergency break when the latency becomes too high. So I had to split it, but for some reason there was no splitting or cloning operator in the standard crates for streams. So I built one. I tried to build one myself. I was not the first one. There were already other people who did the same thing. But yeah, it was a learning process for me as well. So the latency, the problem here is that the latency stream is owned by only one thread or task at the same time, and we can't, this code will not compile because we cannot share it just like that. So what we can do then is we create a fork operator, and the fork operator will allow the outputs to be cloned. So we have actually 3 different streams here. Right? We have the we have 2 different. It's just important to know as soon as you fork, you already have the first clonable stream. And then we clone it once and send that one to the emergency braking mechanism or something like that. The architecture of this operator looks a bit like this. So you have the input stream, and you call fork, the fork operator on it. You get a forkable stream, and then you can clone into, for example, 2 clones, Alice or Bob. And Alice is a bit slow. Alice has only consumed A and B, but not yet C. And Bob has consumed A, B, and C. And because of that, you have to cache the C in a ring buffer. So the architecture looks quite okay. There is a queue, and you share the queue among different output streams. However, there's some issues if you start thinking about it. So if Alice polls her clone, her output stream, and the output stream forwards this call to the input stream, and the input stream is not ready, then Alice has to go to sleep. So this is what I show here. So Alice first polls, she polls the input stream, so 1, and then gets pending. But then Bob is polling, and Bob suddenly notices that the input stream is ready. Then Bob has to know that Alice was sleeping and wake her up and give her a copy. And Alice should be the one who receives the new item the first, because she was the first to poll the input stream. So to get this right, I started ending up with writing a lot of unit tests. And one thing I used a lot in these tests was barriers. So barriers are a way to synchronize different async tasks or threads by forcing them to wait until all the others in the group have initialized. Because as a simple optimization, for the cloning operator, I only make values available for clones that actually have polled at least once. So I needed to execute this initialization, and for that I used barriers. So a barrier, for example, a 3 barrier will wait for 3 tasks to wait. So first, the send task will, for example, start awaiting. Then the first consume task will start waiting. It's not enough, but as soon as the second consume task starts waiting, the barrier is broken and the barrier is crossed. It's a kind of useful concept, this barrier. And the nice thing about using barriers and not sleeps or intervals is that you can easily convert this into a benchmark to see how fast is your implementation. And you could use multiple synchronization points as well. So the way you use the barrier is by wrapping it in an arc, and then you share it among the different consumers. You create your output streams using your favorite operator, and then you move the barriers, the clones of the arc of the barrier, inside the different tasks. You do your initialization, setup task, and then you wait for the barrier. And as soon as 3 are waiting, you can start sending input from the send, the input task. And you do try join all. If something goes wrong, you get the panic. What are some general principles when you're building your own stream operators? Streams are cool. It's like functional programming, but they are really only appropriate when there is some kind of asynchronous data flow. If there is no async data flow, you probably shouldn't be using streams. Also, don't make your pipelines too long. You still have to respect the other conventions for writing good code. So functions, bodies not too long, descriptive names, the typical things. And also something you need very much is unit tests to really test the behavior of the output streams compared to, for different implementations, different versions, and benchmarks. And for the benchmarks, I discovered this great criterion that is very cool because it can tell you whether any optimizations you do are actually relevant or not from a statistical point of view. For example, you could make a tiny change in your code and suddenly things look faster, but actually your sample size is not large enough. And criterion will tell you, oh, it's actually not relevant, this improval. And then there's also a thing, if you start working with many, with 1 to n stream combinators or complicated stream combinators, you will start using state machines at some point. And something I recommend for state machines is that you don't try to reduce the amount of states too much, because if you start to compress everything in a small set of states, you start to have to need a lot of options, and handling those becomes quite messy. Okay. Do you have any questions for me? You can ask me right now, and otherwise you can send me an email, or these slides are also available on GitHub. They are written in Typists. It's a program that you can use written in Rust to generate technical material. It's a bit like LaTeX, but yeah. Do you have any questions?
All right. Thank you very much. I'm going to the first questions. I saw, yeah, give it up. Okay, I saw a question in this corner. Okay, can you please let me, real quick, thank you very much. There you go.
Thank you for the great talk. So I was wondering, with the barriers, so you have the stream coming in, and you split it into a stream for the UI and for the backend, and both will stop processing until the barrier is crossed.
Yeah.
Does that mean that the mistake in the UI processing can make the emergency brake not be triggered?
The barriers were just for tests, not for production code.
Ah, right. Okay.
Yeah.
Thank you. So how would you do this in production?
You mean dealing with the UI crashing and the backend not?
Forking a stream in a way that they become independent?
I haven't tried it yet. Like the consequences when you would apply this for a train, for example. Yeah, of course, I wouldn't use a barrier, and it completely depends on the use case. Can't really say how to solve it in general.
I understand. Thank you.
Thank you very much. So, any more questions here in the audience? Raise your hand. Okay, over there. And I'd like to ask if you can pass it around again. Thank you very much.
Well, thank you for the talk. I was wondering, you mentioned earlier in your first approach to the method about dealing with unpen that you were going to put a box around it to go around the problem.
Sorry, can you speak louder?
Sorry. I was saying that in the first approach, you put a box around your stream to go around the problem.
Yeah.
Wouldn't it be kind of a performance issue when you have to deal with a lot of data due to the fact that you are using an extra pointer instead of just telling the fact that the stream can be only applied on unpin data types so that it actually performs better for huge streams of data?
Yeah, in production code, I recommend to, where was it? Here, this pin project crate. This one is probably better from a performance point of view because it's more, I think it does this without pointer indirection. Okay. And I just used the box because
Thank you very much. Thank you. Any more questions for Willem? In the audience, I see you in the front. Coming up. There you go.
Yeah, thank you. Anyway, I mean, when you when you fork the stream, it seems like you are trying to actually not duplicate the data. And it feels like it really needs to hold a buffer because otherwise it would really require this synchronization between the readers. Mm-hmm. And do you plan to, like, I mean, you said that you were planning to use that, but you haven't come to use it? Or am I wrong?
Yeah, I just, but it was on a previous job. And towards the end, I started exploring streams. But of course, cloning streams is not that useful from a practical point of view. It was more a way to learn more about asynchronous Rust and functional async programming. But one way to use it would be, for example, with this latency one for the UI and for the backend. Maybe there it could be useful.
Oh, yeah, okay. Thank you.
There's one more question in the chat asking, have you used your streams also to issue commands to the train?
Yeah, you could do that as well. But yeah, then you have to use something else. Then you have to use the opposite of a stream, which is a sync. But that's a bit different. Then this is more about the output.
Yeah, got it. And was the same person, by the way, who asked if they issued comments to the cars in the previous talk. So I have the feeling they want to talk to those vehicles in some way. All right. Any more questions here in the audience? Raise your hand. If not, I want to thank you very much for this talk. Thank you, Willem. Give it up. Lots of positive feedback in the chat, so really good talk. This is now the last session here on the side stage. So we have a closing keynote over at the main stage with Konrad Erwin. Thank you very much for being with me. Thank you for filling up this room so many times. This was great. See you upstairs.